empty today, so everybody will not receive their certificate. I'm joking. So we have Steven again with his second lecture.
Hello, okay, can you hear me? Okay, good. Okay, well, good morning, everyone. Thank you for being here in the rain and the tiredness at 9 a.m. So, yeah, so this will be the second lecture. Just to, let's see. So this was the plan of the course, and so we got through most of this, we got through most of what I wanted to talk about the first class, and so today we'll just finish up a little bit of the first lecture, and we'll go on to the second lecture, and I wanted to talk about photonic quantum information in optical fibers, in particular in next generation optical fibers, and this is kind of directly related to work which we do at the Universidad de Concepción. So the class finished yesterday afternoon. I was showing this slide here, and I was telling you that you have this hierarchy of quantum correlations. So entanglement is not the full story. So you have you can consider, say, the correlations between two systems, and you can treat them as quantum systems using all of the formalism of quantum physics which we know and which we've developed, or which has been developed. So that's one type of correlation, and you can make a model for those types of correlations. You basically say, okay, a state is entangled if I cannot write it like this, which would be a general expression for a separable state. Daniel Filinto did me a big favor yesterday by going through Bell's inequality in a little bit more detail. And so what he was talking about was this type of model here, where instead of using all of the formalism of quantum physics to describe my systems, I'm just going to treat them as black boxes which have some classical inputs. So maybe I have a classical bit which will decide what type of measurement I'm going to do on the system. So it's just a general input. And then I have some classical output bit which would be the measurement result. And of course, I'm talking bits, but you can generalize this to higher dimensions and so on. And then, so if you have correlations that cannot be written like this, these would be what are known as local realistic correlations. So basically, you have a probability distribution here in A, another probability distribution for some output in B, and those are linked by some variable lambda, which is the hidden variable which we don't know, and so on, which Danielle mentioned yesterday. So again, nature is nature. It's not that the physical system itself is changing, it's our model for those correlations is changing, right? So it's kind of the information we are applying to describe these correlations that we're changing the models. So then the intermediate correlation, which I mentioned here yesterday, is steering, which is where essentially you treat one side as a black box and one side as a quantum system, and you can say some things about that. So these correlations form a type of hierarchy. So typically it's easier to show that a system is entangled than it is to show that it would violate a Bell inequality. And then steering, of course, is somewhere intermediate. So I showed you this graphic for the Werner state. So if I take a state that's a class or a mixture of a maximally entangled Bell state with identity, so identity is just white noise here, so just background counts. And this mixture is done with this weighting parameter P. You have this, say, spectrum of correlations. So when P is small, so I have very low portion of singlet state, of Bell state, the state is separable. When P is 1/3 or larger, I can show that the state is entangled, and so you can use entanglement witnesses, and actually you can calculate it using entanglement quantifiers. When P is equal to 1/2, you can start to see EPR steering, so you can violate this model for steering correlations, and then when P is even larger at 1/√2, you can violate Bell inequality with this type of state. So yeah, so this state is a really nice. Shows really well how these correlations form this hierarchy. But this is something that's general. It's not just particular to the Werner state. In general, these correlations form this hierarchy. And so what's really interesting about that, and something that's, say, within the last, I don't know, 10 or 15 years in quantum information, is that these correlations are linked to tasks, right? And now more in particular to the different security you have in tasks. So if I'm going to use entanglement as my resource to do some sort of, say, communication protocol like key distribution or teleportation or whatever, this is what are known as, this would be a device-dependent protocol, Why is it device dependent? Because I'm using quantum physics to describe my device, so I have to characterize it. If I say I'm going to do a measurement in the sigma z basis, I have to characterize my measurement device so that I know it's measuring in sigma z, right? Or I'm going to measure in sigma x or whatever. So it's device dependent in that sense. Your devices are well characterized, and you trust your measurement devices that they're doing what you think they are. Keep forgetting I have this control. Bell non-locality, on the other hand, well, we didn't do any of that. We just looked at the systems as black boxes with some input, some output, and we have some output statistics, and that's it. The only thing that's really assumed in Bell's inequality is you have no signaling between the devices. So there's no, the devices cannot communicate between each other, at least before the measurements happen. And so this is really nice in the sense of, say, protocols that give you some sort of security, or like, say, key distribution. Of course, you want to assume as little as possible. I mean, key distribution is something you're going to use to do cryptography, right? So in cryptography, you generally want to assume as little as possible about your device, be it a classical device, a quantum device, whatever. So this allows you to do what are known as device-independent protocols. So you're not even really assuming that the device is well characterized, or, I mean, so this includes the device can be, say, malfunctioning, it's not working as you think it is, you think you're measuring sigma x, but really, for example, it would be really bad to think you're measuring sigma z and sigma x, but really you're measuring sigma z twice, right? That's something that in entanglement that would give you, say, a false positive, but in Bell's inequality you would not violate, right? So it's kind of built in this protection against malfunctions. Also, I mean, if we discover someday that no, there's something beyond quantum physics, right? There's some other theory that, I mean, maybe quantum physics is like just a piece of the picture, but really there's some more ingredients that go in that we're going to discover eventually. Well, since we never assumed that quantum physics was necessarily valid here, it's not going to affect our device-independent protocols, whereas it would completely or possibly rewrite the whole story of entanglement. So, I mean, that's maybe far-fetched, but that gives you some peace of mind, let's say, if you want to do cryptography with these types of correlations, right? And then, of course, steering gives you something in the middle, which is known as one-sided device independence, because one side was a black box, one side was a quantum system. And so that's interesting because you have, so say, partial security. The problem here, actually, I guess I have this written here, is that, so in terms of how much you trust your system, let's say, your trust increases as you go from non-locality as, say, zero trust up to entanglement, or, say, very little trust, being more realistic, up to complete trust. And then, of course, there's no free lunch, right? So the downside is it becomes more and more difficult to actually see these correlations without any, say, loopholes, right? So particularly the big thing here in doing experiments like this is how much efficiency, your detection efficiency. So if you have some source emitting entangled photons, let's say, and you're going to detect them, how many of those photon pairs do you actually detect? I mean, that depends on how efficient your detectors are, how well you can collect the photons and put them into your optical fibers or whatever, how losses in your system and so on. So it's quite difficult. So EPR steering is kind of interesting in that regard because it's somewhere in the middle, so you get some device independence, but it's not, say, as difficult. And in fact, conclusive EPR steering experiments, just demonstrating this effect without any loopholes, were performed a few years before, even though this type of correlation has been known since only 2007. It was demonstrated, I think, experimentally with zero loopholes in 2012 or 13, more or less. So, 5 or let's say less than 10 years. Whereas Bell non-locality has been known since 1965 and was only demonstrated in 2016. So it's quite a bit more difficult. Yeah, so you have different protocols that are kind of associated with these things. There's also something which I'll talk about in a little bit later called semi-device independence and so on. So my point here is just to show you and give you this kind of overview about how these different types of correlations or different things you assume or the kind of model which you do to describe this fundamental thing of your system, the correlations, I mean, can lead to, let's say, practical protocols that give you some benefit related to others. So, yeah, so Danielle kind of walked about the Bell inequality. I'm not going to talk about it. I just want to say, so in this device-independent model, which is really kind of the holy grail, let's say, in terms of QKD these days, is you want to you want to have some sort of key distribution system between A and B, where your model is this. So you have some black boxes, I don't know what's going on. And of course, the Bell's inequality was already formulated like this, and so you can kind of adapt and tweak the Bell inequality to use it in, say, efficiently for QKD. And so you have using basically, as Danielle showed yesterday, you have some conditions that the correlations here should satisfy if they're linked by some local realistic model. So being linked by a local realistic variable is basically saying, okay, someone has information about the correlations. So if I violate this, it's basically I'm saying, okay, no one can have any information about these black box correlations, and so I have some privacy and so on when I make observations. So the premise of this device-independent QKD is that, okay, if I can show that A and B violate a Bell inequality up to my satisfaction, well, that must mean that there's no eavesdropper. No one can have any information about the outputs of the devices because the eavesdropper would ruin that violation. So basically proving this violation and saying, okay, no eavesdropper, or I can limit the amount of information an eavesdropper could possibly have, right? And so if I know that, then I can apply different protocols to remove that information. And so, yeah, so this, I'm not going to get into any details more about this, but it's interesting that you have this direct link between, say, Bell inequality, these non-local correlations, and the security of QKD. And it does not depend on the equipment functioning well. So that's really interesting because if you look at, I don't know if you've read any of the documents, say technical documents of standardization agencies or government agencies talking about quantum technology or QKD in particular, one of the main criticisms is that, okay, in theory, it's secure, but in practice, it's not secure at all because you have to have detectors that, I mean, you're introducing all this new technology into the cybersecurity stack, single photon detectors or some kind of detector, optical fibers, photons or light has to propagate through these sources, so on, and these different protocols, which you have to implement in practice. And so it's, getting you're getting a lab experiment to work like the theory says is difficult. Now making this happen in the real world where you have, you're trying to use, say, fibers, you're sharing a fiber with telecommunication signals and so on, it's really a mess. And so the big criticism that you have theoretical security, but you do not have what's known as implementation security. So actually implementing this is much more difficult than the actual advantage that this theoretical security gives you. That's kind of the summary of a lot of agencies such as NIST and so on. In fact, there's with all this work in QKD that's going on, and even a lot of standardization work and so on, there's really, I haven't seen any government security agency saying, yeah, QKD is the way to go. So it's like, it's a struggle. So I think one of the hopes of many scientists is that, okay, DIQKD will maybe change this a little bit because it gives you a little bit more implementation security in the sense that it doesn't matter if my device isn't working right, then the system won't work. Then I at least, like, if the device doesn't work, I won't share a key. So, oh, sorry. I wasn't being tracked. Hello? Okay. Hello. Thank you. Yeah, so that's the interesting point here. So it's kind of, it's a beautiful thing, the fact that these different correlations give you different security levels, let's say in QKD. And it's also really nice because it could possibly solve this really practical and crucial problem, right? So just to give you a little sense, so this is kind of one of the, so as Danielle mentioned yesterday, so the Eckert protocol showed how you could, which back from 1991, showed how you could use Bell inequality for QKD. But and there was some hint that you had this idea of device independence. But these papers here, well, there's one in 2004 and then this one in 2007, really started to show this formally how you have this device independence and so on. So this is fairly new type of ideas. And basically, so the price you pay here is that you have, let's say, much lower key rates, right, and much more requirements in terms of how much errors you can allow in your key. So as you're doing these QKD sessions using this entanglement or using entangled particles essentially and violating Bell inequality, you're going to pay a price in the sense that you can't have too many errors, or you can allow less errors, and you're going to have a lower key rate. And so in practice, so there's only 3 experiments that have been published so far. I heard through the grapevine that there's a new experiment that will, a very long distance, very impressive result, but I haven't seen it on the archive or anywhere yet, so I won't mention it really. But so the 3 experiments that were done, 2 of them use this, what are known as event-ready platforms. So these are actually, well, ion or atom traps, right? So you have individual single photon emitters, so an ion or an atom here on each side. And so, as Daniel mentioned in his talks, you can excite these so that they will each emit a photon. You collect these photons in optical fibers, and then you send them to this central station here, where you do a Bell state measurement. So so these photons are entangled, their polarization with some internal degrees of freedom of the atoms or ions here. And then you can do this Bell state measurement here. And so basically what you're doing is, so you have an entangled state between the atom ion and the photon on each side. And so when you do this Bell state measurement to the photons, through entanglement swapping, you end up entangling the 2 atoms or 2 ions, right? And so this is known as event ready because basically when I see the proper detection signal here, as I talked about yesterday, so I project on one of these Bell states, which I can observe, I know that the ions or atoms are ready, right? And then you can measure them individually with really high efficiency. So the reason these event-ready setups are nice is because I can say, okay, I have good entangled states, and I know I can measure them properly with the readout mechanism here in these systems. So, so this I think, is really like, for DIQKD, this is really the way you have to go. So there's several groups pursuing this in the world. So this is the experiments. This is actually from a review paper, but the 2 experiments, one was done in Oxford and one in Munich. You can see the story is not so nice because, well, what do they have here? Fidelity, so those are really good numbers. The rate is very low. So the distance between these 2 emitters in the Oxford experiment, which were the trapped ions, was only 3.5 meters of fiber. The ions were actually only 2 meters apart. So you're doing QKD from one optical table to the other, presumably. So it's not, so it's really proof of concept. And then the Munich experiment, they were actually 400 meters apart, and I guess there were 700 meters of fiber. So it's, maybe more realistic. But you can see the key rates are really low. This is actually, so here you have 100 bits per second. Now I'm not sure if this is event rate or key rate. And then in Munich, it was even less. Let's say, well, 1 over 82 hertz, so whatever that is. So it's really low rates, not so large distance, and the reason that is because you have to have really high detection efficiency. And so basically, here I mentioned you can measure each individual system with really high efficiency, but you have to you have to have this heralding signal. So basically, and the amount of signal I have per second, let's say, depends on how efficient how many photons I detect. So it depends on how well can I collect the photons, how much are they attenuated in my optical fiber, and then how efficient are my detectors and everything to detect them. So, so here you have really high efficiency in each matter system, but the optical system is crucial because it gives you the rate, right? So, yeah, so that's really the limiting factor here, and that's why you have, say, short distances and so on. There was so I wanted to show you that because it also links to the Bell measurement, which we talked about yesterday, which is, again, as I said, so this is, a quantum information processing module, all photonic, but it's used in this quantum network with atoms, ions, and so on. There was an experiment also around the same time using all photonic. So I wanted to show you this as well because it's all photonic, which is the subject of the course. But also, I wanted to show here you have this, say, more modern source of entangled photons. So this is a Sagnac interferometer where you have the nonlinear crystal is this thing here. So basically, you shine the light of your laser in through both sides. And so through one direction, you prepare something like HV, and the other direction something like VH, and you combine them here such that you produce an entangled state. So this is nice because this is probably a waveguide, periodically poled crystal, which is much more efficient. You can really tailor the optical mode, the spatial mode, to couple into fibers, and so on. It's a much more efficient source. And this is, a lot of groups have been using this for about 10 years or so, especially in these types of experiments where you really need high efficiencies and so on. So here, they take the photons. I guess this is actually, well, it's all free space until, it's all free space here, I guess, and then they go into some optical fibers to go into single photon nanowire detectors, which are very efficient. So in this type of experiment, the detection, the overall efficiency you need is something like 90% or 85%, around in that ballpark. So again, that's really challenging because it includes all the losses in the system. And so here, I guess they do put some fibers in here to kind of simulate distance. And you can see they have, say, 20, 80, 220 meters of fiber. But the key rates per pulse are like, what, 10 to the 4, 10 to the 5, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. So I think their repetition rate of the experiment is something like 10 to the 6 or something like 1 million times per second. So you see that they're generating somewhere between 100 to 1 to 100 events per second, something like this, of detection events, or key bits. So again, it's really quite slow compared to what you would want for an actual key distribution, right? But again, it's proof of principle. And so yeah, here's some graphics showing how, I mean, basically, I guess here's 83%. So this is the lowest known possible detection efficiency is somewhere around there. And I think, I forget, there might be some results. I mean, every once in a while a paper comes out and it's reduced a fraction of a percent or something with different techniques. But it's so, I mean, if you detect photons, you know that 80-something%. You can buy detectors that are like that, 80, 90%, but you have all the collection optics as well, so it's quite difficult. The other kind of key point for this type of experiment, which applies to, as I said, to both types of approaches, is the losses in the fiber. So the attenuation of fibers is like 0.2 dB per kilometer. So if you work that out, you say, okay, well, how many kilometers can I propagate until I go from, suppose I have perfect detectors, perfect optics, everything. How many kilometers can I propagate until I go from 100% down to 85% or whatever? It's something like 5 kilometers. So that's kind of the limit, right, for DIQKD if you don't have any other, say, quantum repeaters or anything like that. So it's quite difficult. So, and again, this type of experiment is motivating the development of repeaters and all of this stuff which has been talked about the past couple of days. Okay. Yeah, so that finished what I want to talk about the first class. Now I want to go into talk more about optical fibers and space division multiplexing, which is something we're working on in Concepción. So, so here we go. So I just want to say, are there any questions about this first part? I also wanted to tell you that you can interrupt me at any point to ask questions. Also, if you want to ask a question in Portuguese or Spanish or English or broken versions of any of those 3 languages, I can probably respond. Yeah. Turn off. I don't know if I can, but maybe someone can. Yeah. Okay. Better. Okay. Yeah. Okay. Okay. So this was yesterday. I said this was the motivation of kind of the talk, and also kind of what we work on in our lab. And so now I want to focus again on what's written down below here. So we in our lab we're kind of really focused on working in, say, telecommunications, using telecommunications infrastructure or technology, and we want to basically, okay, if we want to take something to actual real-world use in quantum technology, it's not going to happen tomorrow. It's going to happen, say, 5, 10, 15 years from now, whatever. 3 years from now, whatever number you want to put there. So you want it to be compatible with the technology of that time. I mean, if I build something that works today, I mean, you know this if you've ever had to, say, program an FPGA or something in the lab, you get it all working, and then the new version comes out, it's not compatible with the new version of Windows or whatever, and everything goes crazy. So we want to kind of be ahead of the curve, if you will. So, yeah, so that's what kind of our approach. So, well, real basic thing about optical fiber. So, optical fiber is like a pipe for light. It works on total internal reflection. So basically when the angles, so when light rays propagate, well, here's an image of, say, total internal reflection. So if I have a light ray coming at an angle that's, let's say, larger than this critical angle, it won't refract into the other medium. This is given that the indices of refraction obey this relation. It will reflect in this direction. So, yeah, so this is like the concept behind the optical fiber, so that if I have this kind of cross-section of the fiber, the optical fiber has a core material and a cladding material. It's actually the same material, but you have these different indexes of refraction. And so when I shine light rays in this direction, so this is kind of an optical beam here in gray that I'm focusing on the fiber. And so it works such that the optical rays that are kind of more, let's say, parallel here to the horizontal direction are going to remain within the core. And then the optical rays that are at really large incidence angles here are going to escape into the cladding. So in this way, you can trap light within the core, and it propagates along here. So this is technology from, I don't know, 50, 60 years ago, the basic concept. And of course, this is what telecommunications is based on. You have, say, two main types of fiber. There's a ton of different types of fiber, but you have two main types. One is called single mode fiber. So that means that basically if you consider all these optical rays and kind of an envelope of different plane waves, or different rays, you have these kind of form a single mode. So basically, if I take my laser, I make it into more or less this Gaussian distribution, and I shine it into the core with certain parameters, I can make that exact mode which I created propagate here through the core. And so if I make this larger, or if I put some structure in the mode or whatever, that structure won't propagate through. I'll end up kind of projecting my beam of light into something that looks like this. So basically, there's a single mode that is an eigenstate or an eigen mode of the fiber, and it will propagate, let's say, with minimal loss. All other modes will not propagate any real distance within the fiber. There's multi-mode fibers also, and basically the difference here, the core is wider. So, of course, what defines whether fiber is single mode or multi-mode depends, of course, on the wavelength and the width of the core. So, for example, if I have a single mode fiber for, let's say, 1 micron wavelength, and then I shine light that's, say, 500 nanometers, so half the wavelength, it will be multi-mode. So it will support several different modes of that other wavelength. And so, and of course, you can make these cores, you can have really high multi-mode fiber, so hundreds of modes propagate. You can have low mode, only a few, and so on. And it's kind of playing around with the width of the core and the wavelength of light and so on. So these are the two main differences, right? Yeah, so in your house, if you have fiber internet, there's probably a plastic piece of fiber, really cheap multi-mode fiber that connects from whatever is going through the building into your router, right? They go and install that, so that section is with this plastic multi-mode fiber, but what's in the backbone of telecommunications typically are these single mode fibers. Yeah, so kind of the reason for that is, well, here, so in multi-mode fiber, of course, you can have crosstalk between the modes and so on. So, of course, if you have crosstalk, that ends up as being losses and errors and noise, right? So you don't want that. But in your house, it's only a few tens of meters probably from where it needs to connect to your router, so that's not such a big deal. In the whole telecommunication lines that go hundreds of thousands of kilometers, there the crosstalk is a big deal. You also have to have amplifiers and other devices which have to be compatible with that type of fiber, so that's why single mode fibers is typically used. So yeah, so these are kind of the three main types of fibers in commercial fiber optics, and they're single mode at telecom wavelengths, which is more or less 1.5 microns. So these are the two main types of fibers which are in commercial use. I don't know what I was going to put there. Yeah, so as I mentioned, single mode fibers are used in the real backbone of telecom because they need to be compatible with other devices, and you want to eliminate this crosstalk because that would create errors and noise. And so the way that you multiplex information into the light propagating through the fiber is using the different degrees of freedom of light, or so different degree of freedom of the mode, right? So of the single spatial mode that propagates in the single mode fiber. So you can use different frequency channels or different wavelength channels, right, for multiplexing. You can multiplex in time, you can phase, you can use different polarization channels. There's a number of different things, right? The way information is encoded in those channels, so if you choose, say, a certain wavelength, a certain polarization, a certain, let's say, modulation range, you can then do different types of encoding, right? So that would define a channel. So a wavelength, and let's say I choose a certain wavelength and polarization as a certain channel, and then I can encode information by modulating the light in different ways. So I can modulate in terms of amplitude. So here, maybe if I want to send digital information, say 0011, I can have a lower amplitude oscillation modulation for 0 and a higher amplitude modulation for 1. I can do something that's known as phase shift keying. So here I have just a constant amplitude signal, but when I want to change, so here I have 0, so nothing's happening. I have another, or I have my 0 signal. The next signal is a 0, so I don't do anything. But when I want to change to 1, I flip the phase. So it's really hard to see here, and I'm sorry about that. But here I did a pi phase shift. So I went from a peak to a minimum, and then it came up again. I think that's what's happening there. Anyways, you do a phase shift, abrupt phase shift of the signal, and so that's why it's called phase shift keying. Frequency shift keying is something similar. I have a certain frequency of modulation defined as 0, and then when I want to go to 1 state, I say increase the modulation frequency to represent 1. So all these are different ways you can code information into this light, right? So there's, tons of work on this. It's I don't know, billions, hundreds of billions. I don't know how large the telecom industry is. Enormous, right? But so what's happening nowadays is that you have something that's known as the capacity crunch, and basically the idea here is that the amount of information you can encode into a single mode fiber is reaching its limit, or has reached or has basically left its limit. So this is showing the capacity, so how much information can you encode in a single mode fiber, using light, over, say, since 1980 until roughly 10 years ago. So here are, I guess, different data points of different techniques, and it shows you kind of the different technology that was invented, which allowed for these improvements. So in the beginning, the fibers were improving the transmission. Then in the 90s, they invented the erbium-doped fiber amplifier, which allows you to do amplification of the signal, so that allows you to have more losses and so on, which allows you to kind of compact the information together a little bit more. You have different encoding techniques and so on. WDM is wave division multiplexing, so using more and more wavelength channels, you have more channels, you can transmit more information, of course. And then, but all this is getting, so all these techniques have taken the technology up to the limit here, the capacity limit, which is basically determined by the following. Once you have a certain amount of intensity inside the fiber, you start to have nonlinear effects and just crosstalk, which you can't control, and so on. So there's a limit, which is basically, it's like, imagine you have a hose, and I'm gonna turn on a pump of water through the hose, right? I can put more and more pressure, but eventually the hose is going to burst, right? And so that's essentially what's happening here. You have so much light intensity in the fiber that you have nonlinear effects and so on, which are kind of out of your control, and basically the fiber breaks. Eventually you're going to damage the fiber and so on. In our lab, we use pulse laser sending fiber. We destroy fibers fairly frequently. So that's basically what's happening. So the way, one of the proposals to get around this is that, okay, well now, so if I reach the capacity of a single mode fiber, we'll have to go to fiber that supports more spatial modes. So maybe I have to go to multi-mode fiber or something different. So that's what's known as space division multiplexing, this idea that, okay, I'm going to use all the techniques I have now, but now I'm going to use some more spatial modes to make more channels, and hopefully do this within the same fiber, right? Of course, I can have one fiber, I can put another fiber right next to it, but then imagine you're going to have these cables which are larger and larger and larger until it's not practical either. So the idea is to not increase the amount of fibers I have, but to use the fiber in a more intelligent or more interesting way. So this is space division multiplexing, SDM, and so there's a lot of groups working on this in telecom. We're looking at this in terms of quantum information. So so here's what a single mode fiber might look like, right? You can, of course, go to multi-mode fiber and try to use some of these different other modes. Of course, you have the crosstalk problem and so on, but you can pursue that. Another solution is what's known as multi-core fiber. So in this type of fiber, the fiber is actually constructed so there's multiple cores within the cladding material. So the fiber is the same size fiber, but instead of having all this cladding area, which I'm not even using, I'm going to put more cores within that cladding area. So I'm not increasing the width of the fiber, I'm putting more channels, right? That's one possible solution. You have more exotic solutions, so this is what's known as structured fiber. You have other types of structured fiber. One example is the ring core fiber. So here you have this, you have the cladding, and actually the core is not a single circle, it's actually a ring, and this allows you also to put more spatial modes in the fiber. There's even, some crazy ideas which are being investigated, again, in telecom. I saw this recent review paper, and here, there's groups pursuing this and constructing this in a academic and research level, which is to have multi-core ring core fibers. And so their idea here is, well, here, what's this, 7 cores. Each of these cores is a ring core. So the idea here is that, okay, I'm going to have these data bits. I'm going to do the usual wave division multiplexing, which I do in each fiber. But then I'm also going to use different orbital angular momentum modes, which we talked about yesterday. And the interesting thing about these modes is that these are eigenmodes of the fiber. Because you have this ring structure, if you remember the orbital angular momentum modes, which I showed yesterday, had this, look like a donut, right? The idea is that these donuts, you can make them so they propagate through these fibers. And so it's an orthogonal basis of modes, and so you can then do this spatial division multiplex. And so each core has SDM inside of it, and then you also have the SDM that comes from having several cores. So this is kind of the sorts of things that people are pursuing to really boost the transmission rate of a fiber. Again, we don't work with this type of thing, but in Concepción we do have ring core fibers. Gustavo Cañas in Universidad Bio Bio is working a lot on this, and we have in our lab with multi-core fibers. So this is so I really have to give a lot of credit to Guilherme Xavier and Gustavo Lima, because they're the ones who really started bringing this technology into the lab in Concepción. Guilherme is no longer in Concepción, Gustavo is. And so around 2015 or so, they bought some multi-core fiber and started to play around with it and did some experiments, which I'll tell you about. And they actually wrote this review paper back in 2020 talking about kind of the perspectives of quantum information with this new structured fiber. And there's a bunch of groups in the world looking at this sort of thing. So one thing that's interesting here with these multi-core fibers, it's really kind of conceptually nice because each core is a single mode fiber, an independent channel, right? And so that means that you can construct these fibers so there's no crosstalk between the cores. And the way you do this, well, the cores are fairly far apart. Depending, if you put a lot of cores here, they might get closer together, of course. But if you have, say, 7 or 4, or say a low number of cores, relatively low, they're fairly far apart, and I'll show you the numbers in a little bit. But the other thing is that you can construct the cladding. You can make what are known as trenches. So you have this increased refractive index at this place of the core, and then just outside of it, you can really lower the refractive index around it, which doing this what's known as trenching. And that basically, so you have kind of evanescent wave leaking out of the core, but then you make it so that this evanescent wave can't pass into the rest of the cladding. So you basically trap it on either side of the core. So you really reduce the coupling between the cores. So for all effects, these cores are independent channels. Which is nice because, okay, if I know how to work with a single mode fiber, now I have several single mode fibers. Great. So this is what I'll talk about mostly today and on Friday, and this is what we work with mostly in our lab in Concepción. As I mentioned, in Concepción, Gustavo Cañas works with this type of fiber, and we're doing some things with that. These are really nice, as I mentioned, because they couple to these orbital angular momentum modes, which people really like for, say, free space propagation and things like this. Okay, so I'm going to talk about quantum information with these multi-core fibers. So how do you encode information, or how are we approaching it? There's several different ways, but so again, we work with, say, single photons. So we're going to use this linear momentum coding, this path encoding, which I mentioned. So basically, I'm going to find different states, right? So some basis of states with these linear momentum modes. So basically, the state 0 is when I have my photon in mode 0, and so this is a single photon. So if the photon's in mode 0, I call this state 0, meaning it's here, and there's no photons in any of the other modes, and so on and so forth for the other states. So you can, if I can produce a kind of superposition state of these different possibilities, I can prepare a general state like this, right? Real basic idea. And so, of course, each of these linear momentum modes I'm going to associate to some core of the fiber. So this is, in our lab, we work mainly with 4-core fiber. So you have these states 0, 1, 2, 3, which, again, the 0 state is when the photons propagate through this core. The 2 state is when the photons propagate through this core, and so on. So here's an actual image taken with a little fiber microscope and a cell phone of what it actually looks like. So these cores here are standard single-mode fiber cores, so it's 8 microns. So that's the standard size for SMF-28 fiber at 1.5 microns. So it's single mode for 1.5 microns. And they're separated by about 50 microns. So they're fairly far apart, and so you have low crosstalk, and also, depending on the fiber you buy, it can have this trenching as well. So, okay, you might say, okay, well, why? Great, you have these new fibers, wonderful, but why don't you just use 4 fibers instead of 4 cores in a single fiber? I mean, I talked about why you'd want to do this for telecom, because I don't want to have cables that are getting larger and larger and larger. Of course, we want to follow the trend, or we want to be ahead of the trend in telecom when we're thinking about doing quantum telecom or whatever. But there really is a reason why it's interesting to have 4 cores within the same cladding instead of 4 different claddings with a core at each one. And that's because you expect, at least, that because all my cores are close together, they're embedded in the same material, that I should have more stability in terms of phase stability. Because if I have any temperature fluctuation or bending or whatever, what have you, with the fiber is going to affect all 4 cores more or less equally, right? If I have 4 different fibers, they can each move, and I mean, someone can throw one over there, throw one over there. These are completely different effects on different modes of my photon, different states, and so you have a lot of instability. And if you've ever worked with fiber interferometers, you know that they're fluctuating crazily. Here you expect more stability. And so this group in Sweden, I guess, showed this a few years ago. They built an interferometer, a 2-path interferometer. One of the interferometers was made with 2 single-mode fibers, so the basic fiber interferometer which you would build. And the other interferometer, they built the same interferometer. In one instance, they used 2 single-mode fibers. In another instance, they used 2 cores of a multi-core fiber. And so here's the fluctuations over time. You can see that for the two arms that are made of single-mode fibers, I don't know, a few tens of fluctuations within a second. So the phase is changing rapidly. There's no stability whatsoever. Whereas for the single-mode fiber, you see they have some stability over here it's stable for, say, 5 seconds. So this is with no active stability, no nothing, just letting the system be itself, right? And you have some more stability. And again, this interferometer, I should point out, was 2 kilometers long, right? So, of course, on a tabletop, you can have stability for a long time. So this is showing, so I guess they report they have at least like a 10x improvement in stability. So this is kind of what motivates using this for quantum information. So I guess before so let's see, I should mention also, just going back here, so we have 4 core fiber, and I mean the reason we use, as I kind of mentioned yesterday, it's interesting at times to have higher dimensional quantum systems, but not too high, because if I have, I could buy a fiber that has, I don't know, like 60 cores. These you can buy these, or you can ask them to be fabricated for you. But if I have 60 cores, I need 60 detectors, which I don't have the money for 60 detectors, and there's really no reason to have a quantum state that's so large, let's say. So there's some sweet spot. Maybe it's 4, maybe it's 7, maybe it's 9. I don't know. You can decide. But we're interested in this in having, say, a few cores, right? And of course, we can work with all 4. We can work with just 2. There's many different options. If you look, I don't know what the record is for number of cores, but you can go really, really high if you want to, and you have that type of budget. Okay, so some work that was done real early, so I guess almost 10 years ago, 2 kind of seminal results that came out in the same year, roughly the same year. One was by Andrew Shields' group in the UK, and what they did here is, so they took a 7-core fiber, right? They used the center core as a quantum channel. So they did QKD through the center core of the fiber. I don't know, I guess, okay, 53 kilometers. So they're doing QKD here. And then they used 5 of these cores as regular classical telecom channels. So they had really intense signals and were sending regular classical information through those cores. And then they had one core which was used for the data exchange for QKD. So saying, okay, doing the basis reconciliation and other things, processing, communication, which you have to do for QKD. So all this was being done in the same 7-core fiber. And what they were able to do is they showed, okay, the crosstalk is low enough between these cores and the 7-core fiber that they were able to have coexistence of these quantum and classical channels at the same time, which is not obvious because the classical signals, as I mentioned, are so large, and the quantum signal is, you know, a fraction of a photon per pulse if you're doing, say, decoy state QKD. So that, you know, basically the leakage of a single photon from one of these really intense classical channels into the quantum channel would be enough to basically destroy your QKD session. So the crosstalk has to be very, very low. And so here you don't just have one channel, you have 5 of them. So it increases, I guess, 5 times the number, the probability you can have a leakage. So this kind of showed this aspect of these fibers in the sense that, okay, I mean, you have this big problem in QKD is how am I going to send my classical channel, or excuse me, my quantum information together with the classical information in the fiber. I mean, you could say, okay, I'm going to have a fiber dedicated to the quantum channel. Great, but when you try to implement QKD in the real world, that would involve laying out a fiber between your endpoints, a special fiber just for that, or turning off the classical communication channel so you can do quantum communication for some period, which is an option as well. But here they show that, okay, this multi-core fiber gives you this option of using one or some of them for quantum and some for classical. Yeah, so another experiment which came out around that time was this one, which was done in Concepción. And so here they used this 4-core fiber and using this encoding scheme which I showed. And they actually sent 4-dimensional quantum states through 300 meters of this 4-core fiber. And they basically did a proof of concept QKD session in dimension 4 in these multi-core fibers. So yeah, so again, the idea is that they were able to couple light into the fiber in such a way that they produce this superposition state. So this is the input state, and they have these different phases here, which they were able to control. So basically, the photon has an equal probability of being in any of the cores, right? And then they can control the phases. Then, in order to change the phases, what they had to do was, when they were preparing this state to couple into the core, into the fiber rather, they used a micrometer, a micromirror device. So basically, they produced, say, 4 beams of light. Each beam was incident on a different, say, pixel of the micromirror device. And then this micromirror device, basically, the mirrors shift a little bit their position, and so you can shift them a fraction of a wavelength and imprint a phase on that beam. So basically, the light hits the mirror and it returns with a certain phase. So here in this example, these 3 little mirrors are in the 0 position, so nothing happens, or let's say like the 0 phase is defined by these 3, and then this mirror here moved out a little bit, so such that there was a pi phase shift on this beam relevant to the other 3, and then these 4 beams. So you can make a photon that's in a superposition of being in these 4 beams, and then you can put a pi phase shift on this state and then send the photon into the fiber. So this is what they did, right, in this proof of concept. This, of course, is fairly slow. I don't know what the repetition rate of the micromirror is, but it's something like hundreds of hertz or something like that, maybe kilohertz. So that was how they prepared the state. So here's Alice has a laser, some control electronics and so on, produces this state. Here's the micromirror, and here they couple into the channel, which is this multi-core fiber. So this is all preparation of these states, the micromirror, the channel, and then here Bob is going to detect the states. So how does Bob detect these states, these superposition states, right, propagating through the fiber? Yeah, so basically what Bob wants to do is he wants to measure in different bases, which are very similar to the input state, just putting different phases. So he has another micromirror device which he can, again, adjust to do different, imprint different phases and change the basis. So he's able to implement at least 2 different mutually unbiased bases, which is enough to do QKD. And so, but again, these are superposition states, right? So in order to detect, of course, when I detect a photon, I always detect the position of a photon. It arrives at this detector, or it doesn't arrive. It arrives at this detector or this detector. If I have, say, a single photon camera, it arrives at this pixel or that pixel. All photon detection is position detection, right? So how do you, so I have my photons in a let me just go back one, sorry. So my photons in a superposition of being in these 4 modes. How do I detect in that superposition basis? So I imprint a phase, and then I have to do basically a Fourier transform into something like the computational basis, which is detect if it was in this position, or whatever, right? So the way they do this, or the way they did this, is they use a lens here, which does basically the Fourier transform of these 4 spots. And of course, the pattern that you see is going to depend on what the relative phase is. So this is like a Young double slit experiment, but it's with 4 pinholes instead of 2 double slits, or 2 slits, right? So this is the kind of figures you would see, right? And of course, what you can do is you can put a single mode fiber here at the center, or a pinhole detector, if you will, and you can detect if the photon arrives here or not. So if it arrives here with high probability, you have a certain result. If it arrives here with no probability, another result, and so on. So they have this basic correspondence between this interference pattern that they see and the states which they want to project. So again, this is a proof of concept experiment. It worked for that, but it's not so nice in terms of anything practical because, well, the first thing is you're only projecting on one state at a time, right? So if you do an experiment, and you say, okay, I want to project in I don't know, a 4-dimensional basis, but I have to apply one projector at a time. So is it in state 0? I don't know, is it state 1? So always answering yes or no questions. Basically, any efficiency or advantage you gain from having high dimension, you lose because you have to measure, say, 4 times instead of just once. So it's really important, and really to do efficient implementations, right? You need to be able to detect in a basis and measure all of the D results at the same time. So this experiment didn't do that, but it was still a proof of principle of this idea of the multicore fiber. Let's see what else I want to say here. So okay, they were able to show that this was fairly stable, and they measured some state fidelity and had a low, basically all proof of concept showing that you could have this low quantum bit error rate, again, through this 300 meters of fiber. Yeah, so as I mentioned, this single point light detector, with this you kind of lose any of the interesting advantages that, which come from having high dimensions. And of course, another problem here is they had to couple the light from free space into the multi-core fiber directly, so you have really high losses, and so it's low efficiency. But still, this experiment was proof of concept, and it was enough to motivate the search for better tools. And so that's what I want to talk about now, is how do you make this better? So, so we need to have some additional devices, right? So one of them is this spatial multiplexer. So this is a device where basically you can purchase them, or you can try to fabricate them yourself. We buy them. So you can have from the same people who fabricate the multicore fiber, you can ask them to make a device where they butt couple and glue single mode fibers onto the face of the multicore fiber, such that I can send light in through a single mode fiber, and it'll go into the same core of the multicore fiber. So I can do this for 4, 7. We have for 4 and also for 7. I guess you can go higher. So this is really important because it gives you efficient coupling into the fiber, efficient coupling out of the fiber, and it makes this multicore fiber compatible with all the other devices which you have in telecom. So phase modulators, fast phase modulators, amplifiers, whatever you want to use that's compatible with the standard single mode fiber. Now I can couple my multicore fiber into that using this the multiplexer device. So this is important and really practical. The other important thing is, so I want to eliminate the fact that I had to use a lens to measure to make measurements. I can make a multicore fiber beam splitter. And so what is done here is you can take a fiber, you can basically heat it with a current arc, and you can stretch it. And when you do this, of course, the cores come closer together, and you can get them close enough together so you have coupling between the different cores. So basically, if you shine light in through one of the cores, it will, through evanescent coupling, part of it will couple into the other cores. And so this is something, again, you can ask to have fabricated for you. You can try to fabricate them yourselves, and so on. Yeah, so this example here is a 4x4, what's known as a multi-port beam splitter, which are interesting also in terms of quantum information and some, say, fundamental things in physics and so on. So back in, I guess, 2018-19, in Concepcion, they had some of these devices fabricated by a certain company. And so the first question is, okay, what is this device? What is the mathematical operation? How do I describe it on my piece of paper to figure out what it does and what I can do with it? So a student, Tania Garcia, her thesis was characterizing this device. So I said this is a multi-port device. It has, say, n inputs and n outputs, right? It's a unit. We're going to say it's unitary, so we're basically going to ignore losses. Since, as I mentioned yesterday, since we always work in post-selection, we always only consider results where we detect the photon. That means that we can consider all the operations being unitary because losses just are getting thrown into inefficiencies. And so, in general, you have this type of matrix that you want to discover, right? This is what's going to describe your device. This is what's going to, which is in our case is the beam splitter. You can define this in such a way that the first column and first row are real numbers. So which means that all these phases here are 0. This seems kind of basically this is saying I can allow a phase shift here in the input and a phase shift in the output, such that the rows in the first row and first column have 0 phase. This seems kind of, well, why would you want to do this? It ends up being really practical. Basically, what I'm telling you here is you can always define this unitary matrix as being a real bordered unitary matrix, which is what I'm telling you about, times some diagonal matrices which have these phase elements corresponding to input and output phases. This, I mean, almost everyone does this when you're characterizing. If you want to characterize some optical circuit, you generally do this. So how do you determine the elements of this matrix? So the amplitudes you can measure just by the input-output relations. So basically, you can shine even just classical light through one of the input ports, and you can so through input port J, you can see how much of that light comes through output port K, and then you have this the amplitude of this element here. I guess I define this. So the U's here are real numbers, and then you have the phases, right? So so this U is, you can basically calculate it from these intensity measurements, which you normalize once you have all of them, right? So getting the amplitude information is fairly easy. Send light in, see how much came out. The phase is a little bit more tricky, but you can do it. Here, what you can do is you can send light in through 2 ports. So I can split my light beam into 2 with a beam splitter, send part of it through input port 1, and then the other through input port J, and I can change J, right? And so if you calculate, okay, what's the probability that light comes through output port K, given that this movable port, input port was J, it's equal to this, and then, which you can expand, and then you can use the fact that you're looking for the real bordered version of this unitary. So basically, you're saying, okay, I can control or compensate the phase here in the input and the output. So this is 0. So that gives you this type of relation here. So of course you can vary the phase here. So this phi here, I can say move this mirror or something similar, and I can look at this cosine curve, and that will allow me to look at the phase shift that's produced here. But essentially, this phase here, which from the device, will appear as a phase shift. So you can do this for each mode, and you can construct all of the elements of the unitary matrix. So this was done in Concepcion for one of these devices, and the matrix looks something like this. Great, but then you say, okay, well, I don't have to write this. I mean, is there some sort of theory that will tell me, I mean, you have the theory of the beam splitter. I'd like to have the theory of the multi-port, 4x4, multi-core fiber beam splitter. You can calculate, say, a type of fidelity between the matrix that you found and some, say, target matrix or some theoretical, nice, cute model, right? And so that's what was done. And you can say, okay, what's the matrix U hat that is closest to this experimental one? And so it turns out to be something really nice, which is this is known, it's something like this. If you look, almost all of the imaginary parts here are 0, and then all of the real parts are close to plus or minus a half. And so this is what's known as a Hadamard matrix. It's a real Hadamard matrix, right? Which is well known. There's lots of cool properties and so on, and so that's nice. And actually, there's a kind of, say, little physical model you can use to say, okay, why is this a Hadamard matrix and not, say, like a Fourier transform, 4x4, or some other matrix? It's because of the symmetry of the fibers here, of the cores. So, so that's really nice. And so, of course, this tells me, so in theory, now that I know this matrix, I can say, okay, if I enter through port 0, so I write my photon in state 0, I apply this Hadamard matrix, I see that, okay, photon input in state 0 is going to go into this equally weighted superposition of being in core 0, 1, 2, or 3. Great. So now I can do calculations and all sorts of stuff. So this was done. So, okay, we have these beam splitters. We have several of them. They're all, I mean, of course, they're all a little bit different, but they're all approximately equal to this because of the symmetry, as I said. And so what can you do with this? Okay, so you can build, say, 4-path interferometer. Have a beam splitters. First thing you do with the beam splitter is make an interferometer. So you can take this 4x4 Hadamard operation. So I can send light, a photon in, say, in state 0, send it to this Hadamard. I could maybe put some phases here, right, on each mode, which I can do, well, we'll talk about that in a minute, but I can, in principle, apply a phase to each core. So once I do that, I now have this state. And so you see, this is exactly what was prepared in the QKD experiment, which they did. You have this equally weighted superposition state of the photon being in one of the 4 cores, and then you have these phases here which you'd like to control to produce different input states. So this is kind of a kind of generic state preparation system, right? You can, again, apply some more phases if you want, do another Hadamard operation, and have some output states right here. So you could put detectors here, and so you're going to have, so this input state passing through all of this, all these devices, you can work this out mathematically, and you're going to have, say, 4 different output states, or in other words, if I detect the photon at this mode here, it's going to correspond to a projection in output state psi 0, or here psi 1, and so on. And you can say, okay, so this is now like a general measurement system, right? And so here, if you work this out, these are the states here. So this measurement basis is defined as basically back-propagating detection, or say a single photon here, back-propagating to the Hadamard in these phases. This is what you would have for psi 0. So this here corresponds to projection in this basis defined here. And I can change this with the phases. So here, so I can prepare this state, and then I can project into this kind of almost completely general basis, right? So what can you actually, so of course in quantum information, it's really nice to be able to detect in a complete set of mutually unbiased bases. With that, you can do tomography, you can do almost any measurement. Well, at least in terms of tomography, it's sufficient, right? So in 4 dimensions, you have 5 different mutually unbiased bases. So of course, they have 4 elements each. And these are such that if I take any of the elements of one of the bases, and I calculate the overlap with any of the elements of the other basis, they're equal to 1 over the square root of d, which is 1 over 2 in this case, right? So that's the definition of mutually unbiasedness. Now the states I said I could project and prepare are like this in general, right? So of course I can, so here, if you look at this a little bit, you see I can prepare and I can prepare or measure easily in basis M4, M3, M2, M1, but M0, no, because M0 is let's say the computational basis. It's when I have the photon in one of the cores. So, so with the interferometer, I cannot project in basis M0, but I could always remove the beam splitter and change my setup a little bit to project in that basis. So it's something that you can do. It's just, say, not as convenient, but it can be done. Yeah, so the interesting point here is I already have access to 4 of the 5 mutually unbiased bases just by changing the phases. And so, as I mentioned, I can change the phase using phase modulators or other types of devices. So this is wonderful, right? But the bad news is, so the tool that's really missing in this toolbox is a device that allows me to change the phase, the relative phase of the cores within the multi-core fiber. because I'm in this multi-core fiber. I told you it was stable, it's great, but I want to now change my measurement basis, change the state I'm preparing, all within the multi-core fiber, and I want to do this quickly. I want to be able to modulate, I want to send quantum information through a fiber and do QKD and other things. So this is bad. The good news is that, well, okay, this is good news maybe for all of you, because if you could invent this type of thing, you can probably retire, because this, of course, is what's needed also in telecom industry for fast switching and things like this. So if you can figure out a way to change the phases within the multi-core fiber, this is something that's really useful and has a lot of application, right? So we're working on this a little bit in our group, and I'll show you these results are very recent. Literally, Adera sent them to me last night. So here we're playing around with actually basically putting mechanical stress in the fiber, so squeezing the fiber using some commercially available polarization controllers. And so we have this hooked up to a motor. So here he was modulating, basically pressing and releasing really slow. It's about, I guess it's 60-second period here. But still, you can see the mechanical stress is being, the input-output signal, which we're measuring in it says a 2-path interferometer. The output light is being modulated at the same frequency of the stress. So this is kind of really preliminary. It's very slow. You're not going to be able to encode information with this, but we still think it's interesting because maybe we can use this just to stabilize the interferometer. Because I told you if I keep the light in the multi-core fiber, it can be stable for at least a few seconds, or if it's a short interferometer, can be stable for minutes, maybe even hours. And so this slow modulation might not be a big deal. So this is something which we're working on. In terms of how to do this really quickly, I mean, maybe you can make a typical electro-optical modulator for multi-core fibers. It's something we've kind of discussed, but we've never really pursued. So here's I hope one of you can retire on this idea. And let me know when you have it, because we need it in our laboratory. So how do we get around this in order to do interesting stuff? Well, unfortunately, we have to, so this is basically what I told you, what I drew out before. So this is how we do this in the lab now. So here's the multi-core fiber beam splitter, here and here. So the Hadamard transformations which we had, here are the phases. And so to apply the phases, I actually have to couple the light out of the multi-core fiber into single mode fibers. And then here I can use standard phase modulators. And these can operate, tens of gigahertz. They can modulate really quickly. So I can, change the phase, apply independent phase for each pulse of light or each photon that goes through. And so I can have a preparation stage and a measurement stage, or say a set of phases for preparation for measurement. And then, the rest is more or less what you'd expect to couple light into the multi-core fiber beam splitter. We use a demultiplexer. So one setup we have uses just a laser, so an attenuated laser, which we pulse, send into the interferometer. It couple the light from one of these fibers into the multi-core fiber beam splitter, four-dimensional interferometer, and then here at the output, we couple light out of the multi-core fiber into single mode fibers, which are then connected to 4 different detectors. So it's a 4-path Mach-Zehnder interferometer, all in fiber. So this is kind of the basic building block, which of course what you're going to want to do then is put cool stuff here in the middle, right? Because so as I said, this is the state preparation, and this is the measurement. Of course, I want to do something interesting in the middle, which is what I'll tell you about, say, like for the next 10 minutes today, and then next class as well. So this is a general device. We use a weak coherent state input, at least in this first setup. We have to, so because we go into single mode fibers, the phase is going all over the place, as I showed you before, so we have to actively stabilize it. But the really cool thing, which is crucial, is that because these beam splitters are really close to this Hadamard matrix and the overlap is really good and so on, and we can get good stability, we can have really high interference visibility. So it's typically greater than 99%. I mean, we sometimes have 99.7% interference visibility, which is necessary to do some of these kind of challenging protocols. So here's some results from, I guess, like 5 years ago or so. So up here shows you what's happening in the device. So here these are all, each color corresponds to the counts at a different detector. So these are single photon detectors. So if if the stabilization system is turned off, the lights, the counts are going all over the place at a frequency, I don't know, around a hertz or so, I would say, or a few hertz, or a fraction of a hertz. When we turn the stabilization, boom, we can basically make it so that the phase is stabilized such that all the output photons are directed to a single detector here, D0. So typically, in our experiments, we have this stabilization system turned on. We're maximizing the counts at D0 above a certain threshold, and then we will intermittently go and do a measurement. So we'll be stabilizing. We'll say, okay, go do a measurement, apply different phases, run an experiment for a fraction of a second, go back, check if it's stabilized. If yes, continue, do another measurement. If not, maximize the counts in D0 and go back. So you're kind of going back and forth between stabilization and experiment. So here, what was done is in this little yellow region here, so as they were stabilizing, they were going and applying different phases, making the counts fluctuate according to basically doing ramping the phase so that the counts all fluctuate, and you can see these interference curves. So this is basically doing like, you know, the analog of the malice experiment or whatever you have, you basically scanning the phase of an interferometer intermittently with stabilization, and you can see you have these, well, here the visibilities are all above 99% of all the signals. So it's a high quality device, and so this is like the workhorse for experiments which you want to do. Yeah, so okay, I'll just finish telling you, say, one thing which we've done with this. Well, part of this paper, which we published a few years ago, was to do a quantum random number generator based on this, and a high-dimensional quantum random number generator. So as Danielle mentioned yesterday, you can basically use the fact that if I send a photon through the beam splitter, it will randomly appear in one of the outputs, right? So if I just send it through the beam splitter and check if it's here, 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 it will randomly appear in one of the detectors, right? So in this type of experiment, you expect one of the detectors to click with a probability of 25%, right? So basically, you can translate this random detection into the generation of 2 random bits, right? I have 4 possible events, so 2 bits are 2 bits of information, right, to describe these 4 possible events, and these events are appearing randomly. I'm generating 2 random bits per photon with this type of experiment, right? But then, of course, here the question is, if you build this type of thing, and this type of quantum random number generator has been sold commercially for almost 20 years, the question is, well, how do I know that these detector clicks are due, or when the detector gives me a response, right, says I clicked, and the other one says I did not click, how do I know that that's due to a photon arriving and not someone who's hacked the detector? Or, I mean, maybe, I don't know, there's someone sending in some other signal and making this detector click and making all other 3 go blind. I mean, this type of manipulation can happen. In fact, it's been demonstrated. So what you can do is you can basically send light into this device, either through a hole in the box or whatever you want, and you can force detectors to click or to saturate so they're essentially blind. You know they're not going to click, and you can make all this signal here be completely determined by you. So it looks random to the person that's looking at the detectors, but it's not random to you because you're forcing the detectors to click in a certain way. And you can do this in such a way with some pattern that appears random, but really is not. So that's something that there's a few papers where people have done this and actually done this to commercially available devices, right? So as I mentioned, so kind of tying this into something we talked about before with this idea of device independence, I mentioned that quantum physics allows you to basically build models where you don't have to necessarily assume quantum physics. You can just talk about probability distributions. And so, yeah, we talked about this in terms of the Bell inequalities. There's also something that's known as semi-device independence, which you might consider, I mentioned quantum steering is related to one-sided device independence. You could also maybe call that semi-device independence. There's maybe semi-device independence has a broader definition, but the general idea here, and this is something that comes from Martin Pawlowski and Nicolas Brunner, 2011, is that you can maybe make, say, one or some minimum amount of assumptions which you hope are justifiable in some way. What they did in their papers, they said, okay, let's suppose that the dimension of the Hilbert space, I don't know anything about my device, but I know the dimension of the Hilbert space is less than 3, or less than whatever. I mean, that's something you can sort of assume. And so maybe in the interferometer, you can say, okay, I have 4 optical fibers, and so I'm going to assume that the Hilbert space dimension is 4 or less, or something like that. So that's something you can do. You can assume something about the source. You can assume something about the detectors, whatever. Just for completeness, so there's something known as, in QKD, known as measurement device independence, and these are types of protocols where you say, okay, well, people are attacking in kind of the best attacks, or the demonstrated attacks in QKD or in randomness generation are on the detectors themselves. So maybe it's not so bad to assume something about the laser source or my source or the states I'm preparing, but I want to do something that I don't assume anything about the detectors, right? So I want to make it that I can distinguish real photon clicks from someone manipulating and making false clicks. And so that's something, that type of thing is called measurement device independence. So going back to the QRNG ideas, that I want to basically protect myself from this detector manipulation. So how do I do that? So instead of just having the photon going into the beam splitter, into the Hadamard, and detecting it, I'm going to use 2 beams. I'm going to build an interferometer, use 2 beam splitters, and put some phases here. So if you remember, so basically this is like my preparation. Okay, sorry. I made this different. So basically, I'm going to consider these 3 operations as a state preparation, and then the detectors as the measurement stage, right? So I want to basically, I'm going to end up assuming something about the state preparation, but I'm going to treat this measurement stage as in a black box way. And so that's the general idea. So here I'm going to prepare different states with the state preparation device. So I can prepare states which are basically just the computational basis of the photon interferometer. So I can prepare it such that I can make the photon definitely leave one of these output ports with perfect, with 100% probability, assuming there's no errors. So I can know that the photon should be going to D0 or should be going to D1 or D2 or D3. At the same time, I can prepare a superposition state where now the photon will randomly be detected by one of the 4 detectors. So this is the idea. So I can be changing back and forth between these 5 states, right, in this way. And so the idea is that, well, so of course in the bottom state, the output should be random, but in here, I expect a certain pattern of clicks, right? So that means if someone is manipulating the detectors and I'm sending, say, state 0 and someone manipulated so that detector 3 clicked, I'm going to detect that, right? I'm going to see the detector result does not correspond to the state I prepared. And so that's kind of this idea of doing this QRNG in a device independent, or a measurement device independent way. So here, you're going to do an analysis of this where you're going to basically look at the different event frequencies and do this so you assume as little as possible about what's going on. Yeah, so with our collaborators, we basically built this model. It included actually even multiple clicks of the detectors. Since we're using just weak laser pulses, sometimes you have 2 photons, sometimes you have 0 and nothing happens, but sometimes you have 2 photons, so you have double clicks, so you can put that into the analysis as well. And what you want to calculate is you want to look at what's the minimum entropy, which is defined like this, of the output results. Here, PG is known as the guess probability, so it's basically what's the probability that someone could guess what the output is, right? And so you can, in considering these event frequencies, you can calculate the guess probability, and then you can calculate this entropy. So all this is done with some little bit sophisticated analysis, which I don't remember right now enough to tell you about, but it's all done with semi-definite programming. So it's numeric to optimize this, but it's efficient. So here's what, in an experiment which we did, which basically, as I said, we're stabilizing. This is an interferometer, so we're stabilizing it. And when it's stable, we go do some measurements, go back, stabilize, do some measurements. And so here's different rounds. So I guess each of these rounds here is a few thousands or 10,000 events, I can't recall. But the interesting thing here is we obtain a min entropy that's larger than 1. So 1 would be the limit if you had a single bit of randomness per round. So even with errors and imperfections and say this numerical optimization not being, say, quite optimal, we're able to beat the bound for, say, a two-dimensional device. So actually, we have a gain that comes from the fact that we have a four-dimensional system and not a two-dimensional system. And that's what we wanted to show, the fact that you have this increased randomness generation thanks to the fact that you have a four-dimensional system instead of a two-dimensional system. Yeah, so this was published in this paper here. So, all right. I don't want to go to the bell today, but I'm just going to mention one more result. So again, this experiment was basically the same, the interferometer with nothing more in the middle, right? I mean, I told you I was going to put interesting things in between the state preparation and measurement. Here, we used basically just the interferometer. Another application of this interferometer, actually going back to the telecommunications, and again, why it's interesting to develop these in multi-core fiber phase modulators is that you can use this interferometer as a switch. So actually, in collaboration with some telecommunications researchers, we built one of these interferometers to use as a switch in telecommunications channels. So basically, as I said, you can, well, in the QRNG device, we made the photon leave in a certain output. So basically, we're inputting through 0 and sending to outputs according to the phases we apply. And I can do that actually for all the inputs. So I can come in through input N, and I can make the photon leave through output M. So this is a switch, and you can use this to connect systems and so on. But the question is, okay, how fast can you do this? What kind of bandwidth does it have, and other questions like that? Does it support fast keying? So this is some of the stuff we investigated in this paper. And here just shows you, so the kind of main point here is that we have relatively fast switching. I think this is maybe one of the fastest switches for multi-core fiber that's ever been demonstrated. And we have, say, switching on a switching time that's less than a microsecond. To let you know how is this done in practice nowadays, there's some mechanical switches, there's other things which are very slow, on the order of, say, hertz, or let's say, I guess there's some which are maybe almost kilohertz switching. Here we have something that's close to megahertz switching. So yeah, so this is an application of this device, and we built it in, say, something a little bit more professional in an IT rack mount setup and so on, and yeah. So okay, I'll finish there. I guess. And then next, on Friday, I'll tell you more about what we're doing with these multi-core fibers and some quantum information experiments with QKD. Actually, I guess in the colloquium this afternoon, I'll also be talking about this subject, so I'll kind of split some subjects between the colloquium and then the class on Friday with some overlap. Okay, thank you.
In Spanish, Portuguese,
yeah.
French, English.
Yeah.
No French.
Yeah.
Thank you for the lecture. I have a question from the beginning of the presentation. When you talked about APR steering and non-locality, I would like to know a clear difference between them, because the EPR, I had it in mind that it was already about non-locality, so I would like to know the difference between them.
Yeah, so that's a great question. I'll just go back to the slide. It'll probably be easier to. Yeah, so actually, that's what many people thought for. So I mean, just to put it in a historical sense. So entanglement was more, say, like discovered or noticed in 1930 something, right? So I mean, the paper by Einstein, Podolsky, Rosen, and also Schrödinger was in 1935. So it was known that you had this kind of correlation, and some people believed it was real, some people believed it was not real, and so on. 30 years later, Bell did this formulation, right? But even I don't think Bell, of course, he did this formulation of black boxes because he wanted to, I mean, people were debating the validity of quantum theory. I mean, the Einstein, the EPR paper, which talks about entanglement, or it talks about correlations, right, in quantum systems, they were questioning the validity of quantum theory. So the reason Bell did this kind of black box formulations because he didn't want to necessarily assume quantum physics to show that there's this limit, and then he wanted to show, okay, if you, I mean, he was talking about local hidden variables, which is what Einstein, Podolsky, Rosen suggested in their 1935 paper, right? So, so basically these two things were not really recognized as being different until 1989, to my knowledge, which is when Reinhold Werner published a paper showing, okay, some states can be entangled, but don't necessarily violate a Bell inequality, right? But these states still, you can do, say, quantum teleportation or other things like that with them. So that was sort of the first indication. So basically, what Werner said was, okay, not all, some entangled states do indeed permit a local hidden variable model, right? So, yeah. So then, so again, these two types of correlations, and again, these were all started in this EPR paper, right? But then, in around 2007, so Howard Wiseman and collaborators kind of realized that okay, well, this EPR paradox, which people referred to, the type of situation, because the argument of EPR was that, okay, if I can do measurements on this system and they're far enough apart that I don't influence the other system, right? I can basically measure position or momentum or whatever, and I can infer from the correlations what the position or momentum of the other particle is, and I can do measurements with perfect, I can measure X and P at the same time with no, perfectly, right? And so the idea of the uncertainty relation is not true, and so on. That scenario is actually kind of the quantum steering scenario. And so Wiseman and so on realized that, okay, this EPR paradox, or the situation, the context, is not what you talk about when you, or in other words, not all entangled states admit this EPR argument, right? And so they realized this distinction between them. So it's, again, it's with a little bit more thinking and theory and so on, basically what you end up is with this type of, this hierarchy of different ways you consider the systems, right? So here you can see basically this quantum steering is this idea that, okay, Alice is going to do measurements over here, so I'm not going to, maybe I'm not assuming anything about Alice, but a state is going to be prepared on Bob's side, right, that cannot be described like this. So this is this idea that I can do measurements on one side, or through one side I can do measurements or do some sort of manipulation, prepare something on the other side that, say, violates a concept of quantum theory. And that's kind of via this, if I apply this idea of the EPR argument, right? And so, yeah, that's basically this model. So it was really kind of insightful by these, in 2007, to realize that, okay, these are not the same thing, or at least this is something different from the other two. And yeah, I think, you know, a lot of people are surprised by that, and it's kind of not so well known, right? I think quantum steering is fairly well known nowadays, and yeah. So I think you're not alone in being under the impression that EPR is non-locality is entanglement. It's been thought that way. And I should mention, so part of the reason this is perhaps is that if you consider, say, pure states, so if you're doing your quantum course of quantum mechanics, whatever you learn about these things, for pure states they're all the same. For pure states you have correlations, which are all correlations are entanglement, essentially. So this difference only appears when you have mixed states, such as the Werner state, which I showed you.
Thank you for the presentation, Steve. You talk about the multicore for change the channel, and I wonder how you can control that the target channel.
So how I choose which channel
Yes.
it goes to. So with the phases. So again, let's go to the, it's probably easier if I show you the full, sorry. So the switch is essentially this, built in a more compact footprint. But basically, so I have, say, one set of phase modulators here. And I don't actually need all 4. I just need 3. But the idea is if I send light through one of the inputs, here it's in a superposition of all 4, and I can apply phases. And depending on the set of phases I apply, I can force the photon to leave in one of the outputs. So and that works for the different channels. So basically, there's different mappings. So if I have, say, a certain channel in 0, another channel in 1, another channel 2, another channel in 3, and I want to permute them in some way, there's a certain set of phases I can apply that can rearrange them in the outputs. And basically, so here you're doing this like rearrangement of the channels, which depends on the phase, and the phase you can modulate in principle really quickly. I mean, yeah. So it's a fast switch in that sense. It's like some noise right there. I'm about to fall through the. No, there's something there. I was about to fall through the floor. Okay.
Thank you.
More questions?
Again, if you want to talk at the coffee break, that's great too.
Okay. So thank you.
Thank you.